Assalamualaikum, my name is Muhammad Syafik bin Muhammad Salim, EL230888, and with my partner Aziem bin Azhan, EL23024. Today we are going to present about economic dispatch for 40 unit generations with losses. So we go straight to the method that we use for our project assignment. The first method is particle swarm optimization. What is particle swarm optimization, which is PSO? It is inspired by behavior of birds or fish in groups. Each particles equals to one possible solution for 40 power values. And then particles move based on personal best, global best, and also converges to optimal solution over irritations. So we have also the formula, which is A, B, C is equals to cost coefficients for each generator, P equals to power output of each generator, and lastly total cost equals to sum of all 40 generators. So for the PSO algorithm flowchart, we'll start with initialize 100 particles randomly and then evaluate fuel cost for each particles and update personal best and global best, and also update velocity and position, then enforce generator limits for Pmin or Pmax, then iterations equals to 500. If no, go back up. If yes, then straight to output optimal solution, and lastly will end. So this is the coding that we use for the PSO method. So the result we get is the total generation. We get 11,671 megawatt. The transmission loss we get 1,171 megawatt. The load demand is 10,500. The total fuel cost we get is 169,424. So for the optimal power dispatch graph, this graph shows the optimal power output for each of the 40 generators. So we can see that all green bars are between the red and blue dash lines. It means all generators are operating within their minimum and maximum limits. So this method successfully dispatch power to all 40 units to meet the 10,500 megawatt load demand. So for the second graph, PSO convergence, this convergence curve shows how PSO improved the solution over 500 iteration. At the beginning, the fuel cost starts high at around 175,000. Then PSO quickly reduces the cost in the early irritations as particles to find better solutions. By around iteration 400 to 500, the cost stabilizes at the optimal value of 169,424.44 ringgit per hour. Shown by the red dashed line, this proves that PSO successfully converged to the optimal solution. The third graph is individual fuel cost. This graph shows the individual fuel cost for each of the 40 generations, for each of the 40 generators. Generators number 27, 28, and 29 have the highest fuel cost because they have high cost coefficients in their cost function. Meanwhile, generators 1 and 2 have the lowest cost. This is the result of the PSO optimally distributing the load. Cheaper generators produce more power while expensive generators produce less. That's all for me. Thank you.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Aziem. Number metric EL23024. So I'll be explaining method number 2, which is sequential quadratic programming. SQP is a classical optimization technique. It works by breaking the big problem into smaller subproblems and solving them one step at a time, moving closer to the optimal answer with each step. Think of it like finding the lowest point in a hilly landscape. SQP looks at the shape of the hill around you and takes the smart steps downhill until it finds the lowest point. In MATLAB, SQP is implemented using the built-in function called fmincon with the algorithm set to SQP. So for the MATLAB implementation, this is the sixth step of the MATLAB progress, which is the first one is the B matrix generation, the second one is load the generated data, the third one is define the cost function, number four is define the constraint, number five is to run the fmincon with SQP, and number six is collect the results. So for the results, as you can see, the table below is the summary of MATLAB using SQP method. We can see that the load demand we get perfect 10,500 megawatt. So for the total power generated is 11730.7466 megawatt, and the transmission losses is 1230.7466 megawatt. So for the graph, the first graph shows the optimal power output. This bar chart shows how much power each of the 40 generators is producing. The red and green line shows the minimum and maximum limit. So the second graph is fuel cost per unit. This graph shows the cost contribution of each generator. Units with higher output and higher cost coefficient contribute more to total cost. Graph 3 shows the power versus cost scatter. This scatter plot shows the relationship between power output and cost. Generally, units producing more power have higher costs, but the rate depends on the coefficient. So for the last graph is cumulative cost. This graph shows how the total cost builds up as we add each generator. The final value on the right is our total optimized fuel cost. So for the comparison, we do comparison on method PSO and method SQP. So this table shows the comparison between two methods. We can see here for speed, SQP method is much faster than PSO method, uh, but in consistency, SQP is same answer every run, but PSO different answer each run. It's like random based. For handles non-linearity, SQP good, but it is very sensitive. While PSO is excellent in that category. So, in speed aspect, SQP win, global optimal, PSO, marks for this project, PSO, reliability, SQP, real world industry use, SQP, and academic research, PSO. So, overall win is PSO. That's all from us. Thank you.